PID controllers are ubiquitous. You can buy a hardware unit off the shelf. They're relatively inexpensive. You can also use the blocks that are provided in many commercial control environments. The PID algorithm is part of a larger class of control algorithms known collectively as feedback control. Now, the goal of feedback control is usually to keep a measured value near a target value known as the set point. So I've drawn a controller here. You can see a value displayed on its display. And in the commercially available analog PID controllers, which are, to be honest, becoming quite rare because digital controllers have taken over, there will be 3 tuning knobs, proportional, integral, and derivative. And today I'm just going to be talking about how each of those different control actions take part in the controller. Let's first understand how a controller is hooked up to the process that we are trying to control. I've turned the controller around and I've indicated what the typical connectors are that you will see on a real physical controller. Now, let's say we are trying to control the temperature of something like a pot being heated by a heating element. I would have to hook up my temperature. I would need something that I would be able to sense the temperature with, and that would have a wire which comes out, and that would end up in 2 leads that I would connect to the sensor. And then I would have the wire coming out of my element, and that would go to my heating element here. There may be a little power source here that I'm using to actually supply the power. That would be how it is all hooked up. And the way that we would have to think about that in a block diagram form is that we have our controller, so this part, which we will call GC, and this part, which we will call G. On a block diagram, that would appear like GC, which will be writing to G, and we would say that that's maybe the energy here. And then what is coming out of G is the temperature. So this part is connected and this part is connected. So G writes to GC writes to G, which results in a change in the temperature. What we're going to do is we're going to use that change in temperature, we're going to compare it to the set point value. And what we're going to do is we're going to subtract over there and add over there. And this is going to be our block diagram for all of our controllers. And you can really think of this block corresponding to the controller block itself. As you can see, that's got the same stuff hooked into it. You may ask yourself, where is the set point in this? And the set point is actually entered on the front of the controller device. Now, we're going to be talking primarily about the calculations that occur inside of this box. And what's going to be very important to us is figuring out the machinery of this calculation. Now, to keep things general, we'll just introduce a little bit of extra nomenclature. We'll be talking about just Y as the set point, YSP as the set point, And we'll also be introducing the idea that this output from the process is just also called y, and the difference between that set point coming in and the measurement coming in the feedback loop is going to be called the error. And so all of our calculations are going to be written in terms of the controller responding to the error. This is not the only way in which this calculation can take place, but it is by far the simplest. So in order to compare two values, when they are near one another, their difference is low, and when they are far away from one another, their difference is high. So the subtraction calculation is the simplest way of comparing two inputs to one another. It also has the distinct advantage that it's linear. So here is the simplest possible way of responding on the error. So we've got our YSP from before, our measurement, we're calculating an error, and we have the simplest transfer function that we can imagine, which is simply a proportional gain resulting in the control output. So within the theory of linear systems, this is literally the simplest way in which we can have any degrees of freedom in our control calculation. We could imagine, let's say, just a straight feed through, but effectively, if you think about it, that's just a KC of 1. Now you will see in the textbook that this block diagram isn't shown in exactly the same way. Rather, we just have a formula which is that P is equal to P bar plus KC ET. And this calculation is there to highlight the idea that there may be a steady state bias to the control output. Now remind yourself that this block diagram format ignores any steady state behavior. In other words, we've typically rewritten this in terms of deviation variables. And so doing that effectively, the P will fall away, and because we will effectively have done something like this, P bar minus, or PT minus P bar is equal to KC ET. And this whole part here, this is in fact the deviation variable version of P. And that's what we're going to be talking about there. So it's a little bit confusing in terms of the way that it's indicated, because we would like to distinguish the symbols used for these two things, but that's why we'll be able to ignore the bias in most of our calculations when we're working with transfer functions. Now, one of the confusing problems about proportional control, I think, is easier to see with the equation in this form. If we look at what a proportional controller will do if the error were to undergo a step change, in the diagram as it stands in that form, we can imagine that the output would simply be exactly that multiple Kc times the error. So if that error is a unit, then the output will be exactly that unit multiplied by Kc. And that's easy enough to understand. But in reality, we know the controller is actually going to be connected to a system. And the system will respond, and the error in fact will become less eventually if we have chosen all of our gains correctly. And so this is a confusing piece of behavior which is known as steady state offset. And in that case, so let's say here we have open loop, and this is known as the closed loop. And so in the closed loop case, let's say we bring about that step in the error by changing the set point. At time 0, that step is still true, still exactly the same, still of size 1, and the output is still exactly the same of size kc. But the difference is that as soon as we make this step change, and as soon as the controller starts taking action, the error will become less. And why is this? Because the system is now moving towards the set point if we've chosen the gain correctly, and so therefore the error will become less. What that means is the proportional action will become less. And if you think about it, that means we're talking about this thing, right? Because these two things go together. The error here leads to a proportional change. And we're moving back, in other words, towards the original bias position. But we would like eventually for the error to become 0 again. But as the error becomes less, the impetus for change reduces. And so there's an equivalent less change in the action, and eventually, now I'm going to draw this nice and continuous, eventually we don't quite reach the position that we would want to reach in order for the error to become 0. Now please just note that our target is not necessarily to return to the bias position, because at the bias position the output was the original output that we wanted, right, at time 0. We definitely want the output to be different, but we want the output to be the correct output, which will lead to 0 error. And that's not happening because we're changing. So another way of thinking about this is now very mathematical. In fact, we can increase the mathematical intuition here by thinking about the this equation in derivative form, right? So let's say that we take the derivative here, and what will happen is we'll end up just with the derivative of p being equal to kc times the derivative of the error. And now we can see that as the rate of change of the error slows, the rate of change of the proportional output changes slows, and that kind of corresponds with the graphs that we're seeing here. So you can see initially the very biggest action is when the set point changes, and then slowly both of them the rate of change goes to 0. An interesting way of thinking about this is, let's say we have something like a spring where the system is pushing back against us. So let's say we've got a spring at a particular position at time 0, and we're trying to move it to this set point. If we push with a force that is equal to the proportional output, then we can easily see that if we start pushing and we push less, because remember this difference is the error. If we push less as the error reduces, eventually we will even out somewhere in the middle. The second kind of control action is integral control. And this we can see again as the change in my output being proportional to the integral of the error. You'll see sometimes we distinguish between the current time and some dummy variable that we're just using for integration in this way. Now, we can use the same trick that we used to understand proportional offset to understand the way in which the integral will reduce the error to 0 by again taking the derivative of both sides. And there we see that now we are changing proportionally to the error. So the derivative of the derivative of this integral is simply the error itself. And now it becomes clear that while there is a non-zero error here, we will keep doing something to the output. And so the only time where the output will stop changing is if there is no error. And so we can see clearly that with integral control, if we have a normal kind of system, then this will result in the error becoming 0. So that's the math. It's always useful to kind of have a model for how these things work. And my ever-present model for integral is just a closed vessel. And so there we can say that this the integral here is actually the error integrated. And it's a little bit difficult to think about this just as a tank, because obviously when the error becomes negative, that's actually removing stuff out of the tank. But as soon as these balance out, right? As soon as we don't have any error, the proportional amount will remain the same. Now the last one I'm going to talk about is the derivative unit, and here I'm just going to write the formula. So we've got the change being equal to or proportional to the change in the error. And so we can imagine how this makes a certain kind of intuitive sense. It says that we should be taking more action when the error is changing rapidly, and we could imagine that that means it is moving. If it is moving away quickly from the set point, we must change the output rapidly or in a large way. And you can kind of think of this as being an extra add-on that you add on to controllers, because in most cases this is not sufficient. So you can see that if at any point the error stops changing, then we simply obtain the bias output, right? So if we rewrite this with bias on the right hand side, so then we get PT is equal to just the bias plus 0. And so anytime the error stops changing, we stop changing the output, and basically nothing happens anymore. So this is a good add-on to controllers, but it doesn't actually suffice by itself. A number of problems occur with this derivative calculation, and I want to just talk about some of these issues. The first one is that in reality we cannot build this unit, right? So in formal terms, a pure derivative unit is physically unrealizable, and so many times derivative unit will make control appear significantly better than it really can be, because we cannot build this unit. Also, in practical cases, we will always have some kind of measurement noise. And those of you who've been on a plant will know that all of these diagrams that I've been drawing that have these perfectly smooth curves are completely unrealistic, because in real life those curves will contain some random fluctuations and noise. And all of those little fluctuations, if we were to kind of zoom in on one of those fluctuations, that's a very big spike. And this means that the derivative is large. So that's a very large derivative, and that means that this kind of controller, having a lot of derivative action, makes your controller very nervous. You'll end up with lots and lots of very large manipulations, which is completely impractical. So for practical control, derivative control is always used in conjunction with some other control mode. Truth be told, that's the same for PI control as well. The integrating action is usually combined with proportional action. But even more so for derivative, you will very seldom see something like a PID controller. You will typically only see a PID controller. Now, even if we've managed to have a perfect measurement, a perfectly smooth measurement of our output variable, so let's say, in fact, we've got a very smooth measurement of our temperature there. In most cases, our other part of the calculation of error, so remember that we've got the set point and the measurement, which lead to the error. Even if we can make sure that Ym is nice and smooth, in many cases YSP will contain relatively large derivatives. And what that means is, as soon as I make a step change in the input, the error changes stepwise. And if I am trying to calculate the derivative of that, what do I get? I get a very large, infinitely high spike, which we know as the Dirac delta. And this is known as derivative kick. So there are ways in which we can actually eliminate this derivative kick, and that mostly involves changing the derivative term so that we don't use the derivative of the error, but rather that we calculate the derivative of the measurement directly and ignore the derivative of the set point. But this points yet again to this idea that the derivative action is not there really to track set point. It may improve control under certain circumstances, but by and large I would be relatively wary of adding too much derivative action to any controller.